Hi everyone. In this video we're going to discuss the second type of improper integrals, which is the case when we have infinite discontinuities in our functions. And so I have here a couple of pictures to illustrate what this looks like. So basically we're going to consider cases where a function has some discontinuity. Before we were allowing it to have some jump discontinuities, but now we're considering the case where there's an infinite discontinuity, right? So there's like a vertical asymptote where your function is approaching this line, this vertical line, more and more, right? So this is what we're going to call an infinite discontinuity. And in that case, you have to be very careful when you're evaluating the integral to make sure that this area here, whether it's finite or not, right? You need to just be able to figure that out. Right? So, and there are kind of two cases. They're very, very similar. Either your discontinuity is right in the middle of your interval, right? So if it happens inside, it looks a little bit different if it happens on the boundary like this, right? So in this case, we're integrating from A to B, and the discontinuity is right at A. Right? But before telling you how to do this appropriately, I'll kind of discuss how to do this in an example. Um, but the idea is actually very similar. But first, I want to do it the wrong way. So just so you know what can go wrong if you're not careful, and sometimes it's hard if you don't pay attention. You might miss that this discontinuity is there. So an important example to keep in mind. All right, let's consider this integral from -1 to 1 of 1 over x squared dx. All right. So I'm just gonna, without thinking, kind of solve this integral. Go, all right, 1 over x squared, I know how to take an antiderivative of. That's -1 over x, right? Because it's just a power rule. You take a derivative here, you get 1 over x squared. And if we're integrating from 1 to -1, then you plug in x equals 1, plug in x equals -1. Right? If we do that, plug in x equals 1, we get -1 over 1, minus, plug in x equals -1, we get -1 over -1. Yeah, because x is equal to -1. So this is -1 minus 1. This is -2. There you go. That's the integral. All right. So this is not right at all. Why is that? Right. So something went really wrong. Why? Well, pay attention to the graph. Like try to think of the graph of this function, 1 over x squared, right? So uh, from -1 to 1, right? So 1 over x squared, as x approaches 0, this number becomes bigger and bigger, right? If x is very small, 1 over x squared is very big. So the graph of this function actually looks like this. Let me try a little bit better to make it. Right, that's how it looks, and we're trying to compute this area here. That's what we're trying to do, right? But you see, this function is always positive. 1 over x squared is always positive. How did we compute this area and got a negative number? That's very strange, right? So this is definitely not right. We did something wrong, right? And what we did wrong is that we basically ignored the fact that this function has an infinite singularity at 0 inside of this interval, right? And so we can't just compute this integral like this. We need, so the correct thing to do is basically the same strategy with our infinite intervals. You have to chop it off at a point, right? And then, so first you're going to need to compute the left and the right part separately. But then you need to chop it off at a point. If you want, call this point here, I don't know, you can call it C. And you need to chop it off here at a different point. Maybe you want to call it D. And then you just need to compute separately. Send C to 0, right? And send D to 0 and see if that area converges, right? So first you compute the integral from -1 to c of 1 over x squared dx, and then you take a limit as c approaches 0, and it approaches 0 from the left, right? So the way we usually say it, putting a negative sign on top of the 0 like that. And then you compute the integral from d to 1 of 1 over x squared dx. And here you take a limit as d approaches 0, but now d is approaching 0 from the right, so we would write like this as 0 plus. Right? And so you need to compute these separately to see what happens to this area, right? Because this will compute the area, this area all the way up to c, and then you send c to 0 to see if this area is finite or infinite, depending on what this limit looks like, right? So let's do that. Ooh, I don't have enough space here. Let me move this picture here. I can move this over here. All right, so if you do that, then now we're going to have a limit as c approaches 0 from the left. And here we do exactly the same thing. The antiderivative is -1 over x. But now we plug in x equals c and x equals -1 plus the limit as d approaches 0 from the right. And here antiderivative is -1 over x. We plug in x equals 1 and x equals d. But as you see here, this is the limit as c approaches 0 of -1 over c minus -1 over -1, right, plus the limit as d approaches 0 now from the right of the first is -1 over 1. Let's plug in x equals 1. And plugging in x equals d, we have minus -1 over d. But as you see, as c approaches 0, this becomes a very large number, right? And this is from the left. It's approaching from the left, so c is always negative. -1 over c is always positive. So this is going to turn into positive infinity. And here as well, this is going to turn into positive infinity. This limit is infinity. That's the correct answer to this integral. The area under that curve is actually infinite. It's an infinite area. It's definitely not -2. All right, so hopefully it looked pretty similar to what we did with the other improper integrals. Right, so before, if we were integrating to infinity, you chop off an upper bound and then you send it to infinity. Now, if you're integrating along an infinite singularity, you also need to chop it off like that and take a limit as c approaches that singularity and d approaches the singularity, see what happens. All right, and so from now on, you have to be a little bit careful with when you're computing an integral. You need to look at the function that's inside to see if it has a singularity, right, during the interval that you're integrating, right? So 1 over x squared, you can see that it has a singularity at x equals 0, and 0 is in the interval from -1 to 1, so you have to be careful. It's an improper. This is an improper integral. You don't see the infinity on the bounds, but it's still an improper integral. It's an improper integral of type 2, this infinite discontinuity type. All right, let's do one more example. So here's example 2. Does the following integral converge? And if it does, compute its value. So this is the integral from 2 to 5 of 1 over square root of x minus 2. Okay, so from 2 to 5, so here's the y-axis, x-axis. Let me make 2 over here, 5 over here. So you see that this has a singularity at x equals 2, right? Because you're going to divide by 0. And so it's 1 over square root of x minus 2. When x approaches 2, this number becomes pretty small, and 1 over that is very large. So the graph will look something like this. Try again. Okay, and we want to compute this area from 2 to 5. So it's on that second case where our singularity is right at one of our bounds, right? Okay, but the strategy is very similar. To compute this area, we're going to create a new point over here. I'm going to call it A, I guess. And then I'll send A to 2 and try to compute that limit. So this is an improper integral because the singularity, our function has I probably have been saying singularity a lot. Singularity and discontinuity, it will mean the same thing. Okay, so I'm sorry if the words get mixed up, but they mean the same thing. So the discontinuity of this function is x equals 2, and it's right at the bounds. So it belongs to the interval that we're trying to integrate over. So it's an improper integral, and to compute it, we need to take a limit as a approaches 2. I'm going to have it approach 2 from the right, so I'll put a plus sign right there. Right from the positive side, that's what this plus says. Of the integral from a to 5 of 1 over root of x minus 2 dx. Now, you can compute the antiderivative of this function, limit as a approaches 2 from the right. The antiderivative of this function is what? So this is 1/2. If you add 1, it's negative 1/2. If you add 1, it will be 1/2. So it will be 2 times square root of x minus 2. X equals 5. X equals 2. Right? If you take a derivative of this is x minus 2 to the 1/2. The derivative, if you do the power rule, it turns into x minus 2 to the negative 1/2, which is what we have here. No chain rule, you're fine. The 1/2 comes down and it will cancel this 2, right? So it'll leave you with what you need. So that's the antiderivative. And we just, that's not x equals 2, that's x equals a, right? Integrating from a to 5. All right, so this is the limit as a approaches 2 from the positive side. Plug in 5 in there, you get 2 times 5 minus 2 is 3. You get square root of 3 minus 2 times square root of a minus 2. And as a approaches 2, this number here will approach 0. This limit is 2 times root 3. So the area is finite, and it's equal to this, right? So we computed, if it does compute its value, we did, right? So this is a case where this is an improper integral, but the area is actually finite. The area under the graph as it approaches the singularity is actually finite. It's equal to 2 times root 3. All right, one more example. Does the following integral converge if it does compute its value? Okay, so you see this is an integral from 0 to 1 of log x. Let's draw the graph of log x. Okay, so log x, we know that log of 1 is 0, right? It goes to infinity there, and then it's negative before, so it kind of does this. That's log x. And we want to see if this area here is finite or infinite and try to compute it, right? The area above the graph of log, because in this case it's under the... So that's not going to give you the area. It's going to give you negative the area, right? Because the integral is the signed area. So because the graph of log is under the x-axis, we're going to get a negative number. If you got something positive, you knew that we did something wrong, right? All right, so we're going to do the same thing. So again, 0 is the singularity, the discontinuity of our function is one of the bounds of the interval we're integrating over. So you chop it off, call it a, and then we compute the limit as a approaches 0 from the right, from the positive side, of the integral from a to 1 log x dx. All right. Oh, we need to find an antiderivative for log x. I had not prepared that, but it's okay. Limit at a approaches 0. So to compute this, I'm going to do it kind of quick as a scratch. To compute that integral, ln, the antiderivative, you can do an indefinite integral, and then you can integrate by parts. You take the antiderivative of 1, which is x, and then you take a derivative of log x, which is 1 over x. So here you're going to get x ln x minus, right, antiderivative of 1, which is x, this, log x, minus, and then antiderivative of 1 is x, derivative of log x is 1 over x. This is antiderivative of 1, which is just x, so it's x ln x minus x plus c. Okay, so that's our antiderivative, right? It's just x ln x minus x. You can check that it's correct because if you take a derivative here, you're going to get a product rule 1 log x and here plus, you can check it's correct. Let me not do that now because it's going to take too much time, right? But this computation tells us that the one antiderivative of log x is x log x minus x, right? So that's what I'm going to use. And I can even factor here. Will that help? I think so. So I'll write it as x times ln x minus 1, right? I'm factoring out the x here. Plug in x equals 1, plug in x equals a. I'm going to erase this if that's okay. Or at least let me try to scooch a little bit lower to give myself a little bit of space. All right. So here's the, right, took an antiderivative, used the fundamental theorem of calculus. Oh, this is x equals a, not 0. All right, so this is the limit as a approaches 0 from the right. Plug in 1. That's going to be 1 times ln 1 minus 1 minus, plug in a times ln a minus 1. Okay, this here is 0. ln of 1 is 0. And here, a times ln a, that's actually, as a approaches 0, that's actually a pretty interesting limit. And I don't know that I gave myself enough space to compute it. But that limit is 0. You can use L'Hopital. I'm just going to use that fact. As a approaches 0, of a ln a is 0. You can use L'Hopital. For example, you can write it as, one way of writing it is write it as ln a divided by 1 over a. And then you get an infinity over infinity. You take a derivative of top and bottom, and you see that this is 0. This limit is 0. So this whole thing, the limit is 0. What we're left with is, that's 0. Here you get 1 times negative 1, which is minus 1. And that's the answer of this problem. So the area under the graph of log, that area is 1. The integral is negative 1 because the graph is below the x-axis. All right. I feel like I should. I'll leave it there, even though it's a little messy. Okay. But it's the same strategy, integrating from 0 to 1, but 0 is an infinite singularity of our function, so we chop off and send a to 0, right? And see whether that converges or not, to see whether this area is finite or infinite. So I have one more problem. similar to the last problem in the first video, for what values of p does the following integral converge? Okay, so on the last video about the first type of improper integrals, we considered the integral of from 1 to infinity of these functions. And we saw that it converges when p is greater than 1. And it diverges when p is smaller or equal to 1. So let's see what happens now that if we integrate from 0 to 1. Okay, so these functions all look like this. So integrating from 0 to 1, we're right at our infinite singularity. We're trying to compute this area here. So we're going to just chop off, create an a here, and then take a limit. And so this is going to be the limit as a approaches 0 from the right of the integral from a to 1 of 1 over x to the p dx. Now here we're going to have to distinguish the case of p equals 1 again because the antiderivative is not given by the power rule. So let's assume that p is not 1. Then we know that the antiderivative, a 0 plus, antiderivative, it's x to the negative p, so it would be x to the negative p plus 1 divided by negative p plus 1. That's the antiderivative. X equals 1, x equals a. Right? So that's the limit as a goes to 0 from the right. Plugging in x equals 1, this is just 1. So you get 1 over 1 minus p. And then minus, plug in a there, a to the negative p plus 1, divided by minus p plus 1, all right, is 1 minus p as well. And now you see this limit, what is going to happen as a approaches 0? It depends on whether this exponent is positive or not. Right? So if this exponent, negative p plus 1, is a positive number, including 0, so, oh, but it can't be 0 because p cannot be 1. Sorry. All right, so if it's positive, then as a approaches 0, right, if you have a positive exponent here, right, think of a squared, for example. As a approaches 0, a to that exponent will approach 0, right? So when this is positive, then this is going to converge. This is going to approach 0, and then that area is going to be 1 over 1 minus p, right? If negative p plus 1 is positive, which is the same as saying that p is smaller than 1. So when p is smaller than 1, this is positive, and this integral converges. If this is negative, though, when a approaches 0, this is going to go to infinity. Right? Think of, for example, p equals to 3 halves, or even think of p equals 2. So that negative 2 plus 1 is negative 1. So this is a to the negative 1, which is 1 over a. And if a approaches 0, 1 over a will go to infinity. Right? So in that case, it diverges. So when negative p plus 1 is negative, which is the same thing as saying that p is greater than 1, right? So in that case, it diverges. And you can see that, as before, the case p equals 1. Okay, so let me write our conclusions here. So for p smaller than 1, the integral converges. For p greater than 1, the integral diverges. And it flips from the last case, right? So we saw that if we were integrating from 1 to infinity, this was the case that diverged, actually. And that was the case that converged. We'll talk about that. The case when you have p equals 1, here you're going to get a log, right? The antiderivative of 1 over x is a log. And as a approaches 0, the log is going to go to infinity. So this is divergent as well when p is equal to 1. I'm not going to write it down, but it's because log of a as a approaches 0 is going to go to infinity. So p equals 1 also diverges. Okay, and so let me draw a picture of what we have found out. So it's basically that picture, but these functions, 1 over x to the p, they have an interesting behavior. So they kind of look like this, right? Here's 1. And when p, so there's two cases. When p is smaller than 1, or three cases, I guess. When p is greater than 1, oh, I don't have space. So let me just copy that because that's a little annoying to draw. Okay, so let me this, put it here, take this and put it here. This, I'll put it here, and maybe I'll give them, okay. This is going to be the p equals 1. All right. So these functions, 1 over x to the p, they all look like this, right? So that's the 1 right there. When p is smaller than 1, we have figured out that this area here is finite, right? Finite area. So think, for example, what I always think of is 1 over root x, right? When p is 1/2, for example. So the function 1 over root x, this part here is finite, but this part is infinite, has infinite area from what we saw in the last video, right? So it's kind of like skinnier here and a little fatter over here. So it's infinite area from 1 to infinity, but finite area from 0 to 1. So that's this case. While when p is greater than 1, it switches, actually. This part here is finite. We figured out last time, right? So 1 over x squared, for example. Think of p equals 2, 1 over x squared. This part is finite. So it's kind of skinny on this side. But this part we just saw is infinite. Infinite area. Yeah. So 1 over x squared is skinnier on this side, but then it's fatter in here, right? And the p equals 1 case is interesting. It's infinite on both sides. This area is infinite. We just computed. And last time we saw that this area is also infinite. Right, so 1 over x is it's an interesting looking strange function. P equals 1, it has infinite area in to the left. It also has infinite area to the right. But then if you increase p, the right becomes skinnier. That becomes finite. But if you're here on p equals 1 and you decrease p, then the left becomes a little skinnier. That part becomes finite. It's kind of an interesting thing to think about. All right, these integrals of 1 over x to the p, especially from 1 to infinity, will be very relevant for us. We're going to use it quite often. All right, so this is it for this video. I'll see you in class.